Today we are going to be talking about open loop op-amp circuits. So let's start with what I mean by open loop. So for a generic op-amp where we have a non-inverting input terminal denoted by the plus sign, an inverting input terminal denoted by the minus sign, and an output terminal on the opposite side. Let's see. Minimize this. An open loop op-amp circuit is any one that does not contain a feedback loop. So a feedback loop would be something like you guys saw in circuits 1, wherein there was a wire or a resistor or something like that placed between the output terminal of the op-amp and the input terminal of the op-amp. This would be an example, as I have drawn it, of negative feedback, because the feedback loop is connected to the negative or inverting pin. In Wednesday's class, we're going to talk about positive feedback circuits, where we'll have a feedback loop where a resistor or something else will be placed between the output pin and the positive or non-inverting input. So today, we're going to deal only with open loop op-amp circuits. The first one that I deal with let's just put a number 1 here, is something like this. So let's say that I have an operational amplifier. I'm going to take my output at the output pin. I have a power supply voltage VCC plus and a negative power supply voltage VCC minus. I'm going to apply my input voltage Vin to the non-inverting input terminal, and I'm going to apply a constant reference voltage, which I'm going to label Vref, to my inverting input terminal. This circuit is what is called a comparator, or specifically a non-inverting comparator. I can represent this circuit using the practical op-amp model as follows. minus V out, and let's put our ground right here. So this is what our practical op-amp model representation of our non-inverting comparator is going to look like. So we can see pretty easily by inspection that our output voltage in this case is just going to be AVOL, our open loop gain of our practical amplifier. So something on the order of anywhere from 10,000 to a few million, multiplied by our differential voltage VD, where VD in this case is simply Vn minus Vref. Okay. So let me write that down real quick. V out nominally is going to be AVOL times Vn minus Vref. So let's look at something pretty simple, okay? Yes. Yes, ma'am.
I don't remember in the data that you said what's VCC and VCC minus.
So VCC plus is the positive power supply voltage, and VCC minus is the negative power supply voltage. So in a real op-amp circuit, and I thought this was covered in the video for the last lecture, but maybe it wasn't. We'll talk about it in a second anyway. The output of the amplifier can never exceed the power supply voltages. So for instance, let's say that we have AVOL is 10,000 volts per volt. The value of Rn and the value of Rout don't particularly matter in this case. Rout doesn't matter because no current is flowing through it, so there's not going to be a voltage drop over it. Rn doesn't matter because this is a DC voltage and this is a defined voltage, so the difference between them is just going to be Vn minus Vref, so we really don't care about the amount of current flowing through the input path either. So I am spending time defining what Rn and Rout would be in this case is pointless because they don't really do anything in this circuit, okay? So if we used our characteristic equation for our non-inverting comparator, and let's say that we had Vn was equal to 1 volt and Vref was equal to 0 volts, if we used our equation by itself, what should our output be? 10,000, right? Because it's just the gain multiplied by the difference. But that actually can't happen. If we could do that, we could create effectively near infinite voltages at will, which would be fantastic, except that if you recall from circuits 1, a voltage is representative of the amount of transfer of energy. So if we were able to create infinitely large voltages, that means we were able to create infinitely or transfer infinitely large amounts of energy. Cannot be done. So now let's further quantify things here. Let's say that VCC plus is 10 volts and VCC minus is negative 10 volts, right? So I believe in the last lecture, there was something that discussed called saturation distortion, wherein anytime our calculated output value goes beyond, is more positive than VCC plus or more negative than VCC minus, we will see that our output signal in reality saturates to that power supply voltage. Technically, that is only true for what are called rail-to-rail op-amps. For non-rail-to-rail op-amps, it's usually going to be somewhere between a 0.5 volt and 1 volt below VCC plus and 0.5 volt to 1 volt above VCC minus, but that's just too many little moving parts to keep track with. So for this class, we're going to assume every op-amp that we deal with operates rail to rail. So what if we had the following circuit? Let's see, let's scroll back. Here we go. Yes. I can try. I can't help but notice there are lots of empty seats up here in the front that are much closer to the board and therefore much easier to see, but sure. So let's say that we have the following circuit. We have our op amp. Here is our output voltage pin. Here is our input voltage pin. And then we are going to apply a reference of 2 volts. Okay. So how do we expect this particular amplifier to behave if we allow, let's put plus 10 volts here at the positive power supply voltage and minus 10 volts here at the negative power supply voltage? How do we expect this guy to behave if we allow Vn to range from -5 volts is less than or equal to Vn is less than or equal to positive 5 volts? I'll draw a picture here. One, 2, 3, 8, 9, 10, 11, 12. So here is V in, here is V out, 10, minus 10, minus 5, positive 5. And let's say for the sake of argument that AVOL is equal to 2, let me write that bigger, times 10 to the 4 volts per volt. Okay, so we're going to quantify how this guy behaves with a particular reference voltage and then use that to really figure out what's going on with this guy. Okay, so I'm going to start with something simple. Let's say that Vn were 0 volts. Okay, so we're just creating a data point here. So if Vn were equal to 0 volts, what would we expect our output voltage to be based on our governing equation for this guy, right? Which is the output voltage is the gain multiplied by the difference in our signals. So our gain is 20,000. And VD in this case would be 0 minus 2, right? So we'd have 20,000 times -2 is -40,000. Is -40,000 between our power supply voltages? No. So what should we expect our output voltage to be? -10. All right. So what if we had a voltage Vn is equal to really anything less than 0 volts? What should we expect our output voltage to be? Still -10, right? Because as the difference gets larger and larger and larger, our output voltage signal will have a nominal value that's getting larger or more negative than -40,000 or whatever, which obviously exceeds the negative power supply voltage. So we can see, let me use a different color. So we're going to have our voltage will saturate, or excuse me, our output voltage will saturate at VCC minus for all negative values of Vn for sure. Now, what happens when Vn is equal to 1 volt? Pardon? Still gonna, so at 1 volt, if Vn is 1 volt, then we have 20,000 times 1 minus 2, so that's negative 20,000. Negative 20,000 is still significantly more negative than VCC minus, so we still have negative saturation, and we're going to continue to have negative saturation all the way to our reference voltage. Oops, that's not what I wanted, right? So until a voltage that's until Vn reaches a voltage that is very, very close to 2 volts, so probably something on the order of 1.995 volts or something like that, we are still going to see that our output saturates to VCC minus. So let's say we had a voltage of Vn is equal to 2.1 volts. So something a little bit larger than our reference voltage. What's going to happen to our output? Vd is now 0.1 volts multiplied by our gain of 20,000 gives us 2,000 volts, which is still, that's significantly larger than VCC plus. So at a voltage a little bit larger than VCC, or excuse me, a little bit larger than V reference, we see that we saturate up to VCC plus, and it's going to stay there. In between, so for a very, very small window, a little bit below V reference and a little bit above V reference, we are going to see that our amplifier is working in the linear range, where the output is simply a scaled version of the input. But because that linear range is so small, it's going to appear that our output signal abruptly shifts from VCC minus up to VCC plus at a voltage value of 2 volts. So we can look at this guy and we can say generically, our output voltage is equal to VCC plus when Vn is greater than V reference, and it's VCC minus when Vn is less than our reference voltage. So this is why it is a comparator. We get a digital high whenever our input is greater than our reference voltage, and we get a digital low signal whenever it's less. And we can control what values that digital low and digital high has by changing our power supply voltages. So for example, let's say that I wanted to create a very simple analog to digital converter. Okay. So this is a simple design problem, or it's intended to be anyway. You are asked to create a simple 1-bit analog to digital converter, or ADC, where your system outputs a digital high 5 volts when Vn is greater than 2.5 volts and a digital low 0 volts when Vn is less than 2.5 volts. How would we go about creating this? So it's obviously going to require a comparator circuit because we are comparing things or comparing our input signal to that reference value of 2.5 volts, right? So I'm going to start and I'm just going to draw a basic op amp. Plus here, minus here. Here's my output. Here's my input, the in. So what does my reference voltage need to be? Let's start there. 2.5 volts, right? And that's what we're comparing everything to. What does my positive power supply voltage need to be? 5 volts, right? Because when it goes high, I want it to hit 5 volts. So VCC plus needs to be 5 volts. What about VCC minus? 0 volts or ground. And here is VI. So this is the most simple way that we can realize this circuit. You have just completed an op amp design problem. Sometimes they're going to be literally this easy. Nothing too wild here. Now, how can we get a reference voltage of 2.5 volts? So can I go to the store and buy a battery that supplies 2.5 volts DC? So I know of 9-volt batteries. I know, let's see, AA and AAA are 1.5 volts. I'm trying to remember what value quadruple A has. That's what's in this thing. Also 1.5 volts. So apparently A batteries, regardless of how many A's there are, give you 1.5 volts. I don't remember the voltage for a C cell battery or a D cell battery because it's been, I don't know, it's not the 80s anymore, so I don't have to power big old flashlights and crap like that. Coin cell batteries and stuff like that, I don't think are in the 2.5 volt range. So right now, as we have this drawn, we would have to effectively have 2 different DC power supplies, which would be a little bit annoying. But we know enough about simple circuits to where we can figure out how to get 2.5 volts when we have a 5-volt supply bulb, right? What would we do? Just put a simple voltage divider in there, right? We know that our input impedance should be so large that no current is going to branch off and flow. So a better or more easy to physically realize version of this circuit would be, we have a 5-volt supply plus minus like so. Here's where our output is taken. Sorry. kidding me because I took the batteries out of this thing that wants to freak out on me. I put it in backwards. Apparently I did. All right. So even jackasses with PhDs still put the batteries in backwards sometimes. So I have a resistor and a resistor, and here's where I'm going to apply my input voltage Vin. So now my question to you guys is, what value should I choose for these resistors? As long as they're the same value, it doesn't matter, is mostly correct, okay? Let me explain what I mean by mostly correct. They need to be the same value for sure, but they also need to be significantly smaller than the input resistance of the op amp, okay? And the reason for that is if this guy right here is, let's call it 10 kiloohms, this guy is also 10 kiloohms, the internal input resistance of our op amp is usually typically on the order of mega ohms or larger, right? So we should expect that the current that flows through a mega ohm resistor would be about 1,000 times smaller than one that's going to flow through something on the kilo ohm scale, right? But if we chose to bias this guy with mega ohm size resistors, then the amount of current that breaks off and flows through the op amp's input terminals would be similar in scale to the amount of current that's flowing from our positive power supply voltage to ground, meaning we would not get true voltage division as we are expecting, okay? So it's important, things like that are important to realize. I don't know how many of you took me for Circuits 1 way back in the fall and are just now taking Circuits 2. I'm not sure what Davis and Lewis did last quarter, but typically speaking, most of the op amp circuits that you've seen to this point should have had all of the resistors having a value of in the kilo ohm range. Even though everything we're dealing with usually involves resistor ratios, we always wind up putting things in the kilo ohm range because that means that the resistor values are significantly smaller than the input resistance so that we don't see current branching off and flowing into the input terminals. And they're also significantly larger than the output resistance so that when we use them to load things, we don't see a significant voltage drop over the internal output resistance. So kilo ohm size resistors are really the sweet spot for biasing op amp circuits, okay? So in all of your designs and all that kind of good stuff that I'm going to ask you to do, where it's up to you to decide what component values and stuff, things are just generically going to work significantly better if you choose to use kilo ohm size resistors for all of your biasing circuitry, okay? I could further explain why, but we'd have to talk about things like input, bias currents and all that kind of stuff that are well beyond what you need to know to succeed in this class. So this is a better realized circuit for our simple design problem. Now, this is a 1-bit analog to digital converter. Let me just put it here, which means it just takes a simple analog signal, compares it to that reference voltage, and then if it's higher than it, we get digital high. If it's lower than it, we get a digital low. What we're going to learn about in Wednesday's class is a more refined analog to digital converter called a Schmitt trigger, because there is a problem inherent with these comparators that we're not quite ready to talk about yet. So let's move along to circuit number 2. Unless anybody has any other questions that we need to take care of for the non-inverting comparator. Everybody kind of on board? If the input's greater than VREF, it goes high. The input's less than VREF, it goes low. All right, so our second circuit here is V out. We're going to apply, actually, I'll take that back, not ground. Our reference voltage to our non-inverting terminal and our input to our inverting terminal. Okay, so let me scroll up here just a smidge. How does that change this practical model? Inverts the output. So to me, inversion implies a change in polarity. I could argue that in some sense it does, but I'm going to leave this output voltage positive polarity on top, negative polarity on bottom. Like what is literally the physical difference between these? Well, don't even get into how the circuit's going to behave. What physically changed? VN and VREF switch places. That's it. So I would argue then that our characteristic equation is going to be the exact same thing, except that VN and VREF switch places. We don't need to really do a whole lot of further analysis, right? So no need to go through the trouble of drawing our practical op-amp model and all that kind of jazz. This guy is governed by the equation V out is equal to AVOL times VREF minus VN. So let's say that we have VREF is equal to 2 volts. AVOL is equal to 2 times 10 to the 4 volts per volt again. VCC plus is 10 volts. And VCC minus is equal to negative 10 volts. Which of you is smart enough to tell me what my input-output relationship should be for this guy? Here's 5 minus 5, 10. Sorry, minus, that looks like garbage. Minus 10, and we're going to let negative 5 volts be less than VN is less than positive 5 volts again. What should this guy do? Yeah, pretty much the opposite, right? So at our reference voltage of 2 volts, we know that it's going to change from low to high or from high to low because that's what happened the last time. So for sure, we know that at, didn't change color. At our reference voltage of 2 volts, it's going to switch from one state to the other state, right? It's going to go from one saturation point to the other saturation point. So when Vn is less than V reference, just let's pick a point of 0 volts. We have our gain of 20,000 multiplied by 2, right? 2 minus 0, Vref minus Vn. So again, we have an output voltage of 40,000, which is much greater than VCC plus. So we say that it's going to saturate at VCC plus for all values less, and it's going to saturate at VCC minus for all values of Vn greater than V reference. So our governing equation for this inverting comparator, which is what this is called, is V out is equal to VCC minus for Vn greater than Vref, and it's equal to VCC plus for Vn less than Vref. And we could create a practical example for whatever reason and go through it, but it's really not terribly important. So this is open loop op amps. This is literally all an open loop op amp can do. It is actually terrible at amplifying a circuit, meaning that you have no control over the amount of amplification whatsoever. That's what those feedback loops do, is put some constraints on being able to control the amount of gain that is applied to your system. The only thing I could do to make any of these quote unquote harder than what we have just done is, instead of applying a specific DC voltage, say, so if instead of saying V reference was 2 volts, I put a voltage divider network and made you figure out what V reference was based on the ratio of those resistors, which, because you guys are all in circuits 2, which means you suffered through circuits 1 and came out on the other side with a grade higher than a C, I feel very strongly that you can do fractions like a boss, okay? So that's really all we have to do today. Open loop circuits are literally these two options. We either have a non-inverting comparator or an inverting comparator. We can apply our reference voltage either directly with a DC voltage source or using a voltage divider where our resistors are in the kilo ohm range to make sure that not too much current flows and starts messing things up. Any questions? All right, so that's all I've got for today. On Wednesday, we will talk about positive feedback circuits. So we will have 3 circuits to analyze instead of just 2. And then by Friday, when we get into negative feedback circuits, we're going to actually wind up taking the whole class period. So enjoy your extra 25 minutes or whatever. Go grab some lunch or take a nap or whatever. See you guys on Wednesday.